Howdy. Morning, y'all. Thank you for being here. Hope everybody's doing well. I was going to start with a quiz, but I'm missing people, so I'll delay a minute or two to give people a chance to trickle in. Before we get started, anybody have questions about homework or anything else about the class? Sounds good. Um, Current homework is homework 5. That one was originally supposed to be due today, but I extended it to be due tomorrow. So hopefully, if we do have questions about that that are lingering, we can get those addressed at the help session tomorrow. Um, and then, um, yeah. So if there's no questions about any of that, then I will go ahead and pass out a quiz for y'all. So if y'all wouldn't mind going ahead and clearing stuff off your desk, the only thing we'll need is just like something to write with. And as usual, keep these face down and put on everybody's shot mode, please. Alrighty, y'all are good to begin. Good luck. It's just some naming and showing you the units of terms in those point kinetics equations. So if you have questions, let me know. Good luck. And y'all got 5 minutes. Speed run. Good job. Thank you. Alrighty, that's the end of time. If y'all would please make sure you got your names on those and then otherwise pass those forward for me. Hopefully that one went okay. Um, in terms of thinking about preparing for our exam, the point kinetics is like one of the main new models that we've learned about. So that's like that's probably like the main emphasis of like homework 5. Um, and so, yeah, being familiar with that equation, being familiar with the terms in that equation, those are all good things that we want to do. Hopefully homework 5 is getting us more comfortable with those equations and applying both the point kinetics equation and the n-hour equation. So yeah, today we are gonna mostly finish what's the chapter that covers the time dependent stuff that covers like the n-hour equation and the point kinetics and stuff. We're basically about to be done with that. And then we're going to be getting into just a little bit of the next chapter, which is a follow up on the discussion about transients. And it's just talking about a property or a phenomena called reactivity feedback. So we're going to keep talking about those transient plots that we were talking about last time, and then we're going to talk about feedback effects today. So I did want to talk a little bit about exam 2 because that is, whoops, exam 2 is going to be a week from today, right, on the 17th. Um, so I've got just a little bit of information for us to know about that. It's going to be the same format as the first exam. I'm going to get you guys a formula sheet. I don't have it made yet, but either like end of today or end of tomorrow, I'll post the formula sheet for you so that you can start using that to study while you're reviewing. In terms of what numbers of lectures it covers numbers 7 through 12. So that's basically all of the lectures that we've had since exam one. And that's going to correspond to chapters 4 through 7 in Dr. Spetkov's notes. And it's going to mostly, hopefully, after we saw the first exam, we realized that it's very similar to the homework. And if we're doing the homework, if we're understanding the homework, we're not really going to have too many surprises, hopefully, on the exam. So, in terms of like what you should make sure that you are able to do is make sure you can do all of the problems and derivations and homeworks 4, 5, and 6. And if you can do that, you're gonna do really well on the exam. It's gonna be the same exact structure as exam one in terms of like how the problems are broken up. There will also be like one or two bonus points, bonus questions at the end. Um, I posted this document in our Google Drive, which is like another review guide. So if you make your way to our shared drive, you can find that is not our shared drive. You should be able to find it under like ex I don't know why I swear I'm not clicking on that. Okay. Exam materials and then exam two guide. So this is showing like which chapters from Dr. Svedkov's notes I'm going to be pulling questions from. We're only going to be touching the very end of chapter 4, so it's like it's not covering all of chapter 4. It's only covering the new models that we've discussed in chapter 4 since exam 1. So it makes basically the only like derivation or like model from chapter 4 to be aware of is that zero-dimensional multi-group model. That was the thing that we did on homework 4 to get calculations for like K effective and our group flux components for a multi-group problem. So those kinds of questions and are free game because that was starting in chapter in homework 4 and then moving forward. So in this review, I kind of took snippets of the like the most important parts from the notes that kind of complement or maybe have the steps of the derivations that you would need. So like that's showing kind of how we got to the multi-group model and kind of how what the starting point is, how we got to this the zero-dimensional multi-group model, um, and how you can like solve for those flux components and how you can get K effective. So this this review continues in chapter 5. That was where we talked about heterogeneous systems and kind of the discussion between like what properties of the system make us have to consider it as a heterogeneous system, or what properties make us have to consider it as a homogeneous system, and um, things that was the main like kind of scope of chapter 5. So being able to say like those terms in the we talked about the six factor formula. We talked about how some of those terms in the six factor formula are going to be larger or smaller depending on if a configuration is like heterogeneous or homogeneous. Those are things that we would want to know about. We talked about some of the things involving spatial self-shielding. We talked about those group flux disadvantage factors, and we talked about how to homogenize a reactor core to get cell averaged cross sections for that reactor. And that was a big part of that's the main kind of the whole idea about cross section and cell homogenization. That was a big part of chapter 5. It's also one of the main kind of things that's involved with that reactor design problem. Um, so yeah, be aware about the stuff from chapter 5 and any of the things involving unit cells, and any of the concept questions about like difference between homogeneous and heterogeneous systems would be fair game for exam 2. And then the next chapter is all about the point kinetics equations. And so being able to derive the point kinetics equations, understanding that these come about because we're considering delayed neutrons. And so being familiar with the concepts and equations involving delayed neutrons and delayed neutron precursors. Um, this kind of spells out some of the terms that are involved in our so like we took our diffusion equation, our energy dependent diffusion equation, and we modified it so that we can account for delayed neutrons being produced. So that's effectively what this equation is right here. This is how it's written in Stekhov's notes, and it's just slightly more complicated than the version that I showed you guys in class because I didn't use a subscript J to account for different kinds of fissionable nuclides. I was assuming J was one, like we only had one fuel type, like uranium fuel, for example, in which case these summations, like any summations over J, they simplify a little bit. And so that would give you the equations that I showed you in class. And so we took those equations, we wrote them we basically wrote a diffusion equation that included delayed neutrons, and we used this diffusion equation to derive point reactor kinetics equations. Um, oops, sorry, I'm getting lost in all these Zoom windows. Um, so um, Basically, we want to be able to derive the point kinetics equations. We can derive them either using the way that I showed y'all how to do it in class. It was also an exercise, I believe, on homework 5 to derive them, not making the assumption that the reactor was infinite. Either way, if you derive the point kinetics equations, you get to the same point. You get to this set of equations, which is the point kinetics equations. And these are basically the things that are going to tell us how different properties in our reactor, like the neutron density and the delayed neutron precursors, evolve as functions of time. Um, so that's the point reactor kinetics equations. We should be familiar with how to derive that as well as the limitations of that model. Um, so this is kind of talking about what the inputs for that derivation would look like and what the outputs would look like. Um, the next thing that we want to be familiar with is how to solve these equations, and the solving process involves knowing the initial conditions for our quantities that are involved in our point kinetics equations. And so notice how here the point kinetics equations are expressed in terms of the neutron density, n of t, whereas here they're expressed in terms of the reactor power, p of t. Um, when you do like kind of the more sophisticated derivation of the point kinetics equations, what you should have seen on homework 5 is that n of t can actually represent any kind of amplitude function. That means that it doesn't just have to be the neutron density. It can actually be any like integral quantity in our reactor. So you can write the point kinetics equations and replace n of t with the power, with the flux. You can kind of replace n of t with any integral quantity you want, so long as you make the units for your delayed neutron concentration work out. So that's if you were wondering like how did we go from n of t to p of t, you can interchange what variable you're solving for. And these systems end up being well suited to solve as matrices. The general solutions for these kinds of problems, where you basically have a set of coupled ordinary differential equations. The solutions to those are going to, with constant coefficients, the solutions are going to be a sum of exponentials. You have the same number of exponentials terms as you have equations. So if you have capital I, delayed neutron concentration equations and one power equation, then in total we have I plus one equations, and therefore each of the solutions to like P of t and Ci of t is going to have I plus one terms. And each of these, it's going to look like a sum of exponentials. These time constants, these omega k's, there are going to be I plus one time constants that we need to solve for. So if you make these substitutions into the kinetics equations, you can actually get you can basically convert this from a system that has like time derivatives in it to a system that is homogeneous for the solutions that you're solving for. And from this kind of system, if the determinant of this big coefficient matrix is zero, then our system is going to have non-trivial solutions. So that's kind of like the general solving process for finding these time constants. What we did from there is we got the n-hour equation, and that's something that we want to be able to derive as well. It's kind of a skip to the next thing, but the oh, so another thing that you so we're writing these equations with capital I delayed neutron precursors, but we can make approximations to simplify how many groups we consider. So one of the ways to do that is to just assume that you have one delayed neutron precursor group, and that allows these equations to be solved very uh, more simply and doing it analytically versus this kind of equation that you're going to get from this is not you basically can't solve it analytically. You end up getting a like transcendental equation that you have to solve graphically. Um, but if you make the one delayed neutron precursor group approximation, you get equations that you can solve symbolically, and then you can get like analytical expressions for the power and for the time constants. So this is showing how you can do that to get the expressions for these quantities. It's how you can solve the kinetics equations with one delayed neutron precursor group. And otherwise, if you have more, if you're considering like six delayed neutron precursor groups, the equations that you're going to end up with to describe those time constants is this n-hour equation. Um, in the n-hour equation, if you plot it graphically, you get this kind of transcendental looking plot where the roots of these equations correspond to the values of our time constants. And we're going to talk more about that today. We introduced that last time. We're going to talk about that more today, but since this is part of the review, I just wanted us to make sure we're kind of talking through everything here. Um, the prompt critical condition, that's the only thing that's in terms of like the point kinetic stuff, that's going to be on homework 6, and I'm going to post homework 6 today. Um, so we're in that same unfortunate situation where I'm assigning homework 6 today, and you get a week for it, which means it's going to be due on the same day as our exam. Homework 6 is a lot shorter than homework 5, so hopefully it doesn't take the same amount of time that a homework normally takes. Um, there will be some homework 6 questions on the exam, so try your best to get as much of homework 6 done before you come to take the exam so that there's less possible surprises. So like deriving this prompt critical condition and the prompt jump approximation, those are two things that you're going to see on homework 6. We're going to talk more about the different units for reactivity today. And by the way, reactivity is technically dimensionless. So if on the quiz you said it was dimensionless, or if you use any of these funny reactivity units, you would get credit for it. Um, and today and tomorrow, we're going to talk about the chapter 7 stuff. So this is kind of letting you know what we're going to want to know about chapter 7, and that's all stuff that we're going to talk about in the next 2 days. Um, and then at the end, I just gave a list of study questions. These are not questions that you will see, but they are concept questions that are related to everything that we've talked about since exam 1. Um, so like bits and pieces of these things will be involved with your exam. So I might not give you any of these questions as they are, but if you know how to answer these conceptually, you're going to have like the good conceptual understanding that you need to be able to do any of like the non-calculation kinds of questions. These would be good to practice like the multiple choice parts and also the the problems or the like the kind of free response questions. So that's the review. This is for you in Google in our Google Drive. Um, if there's questions about the exam guide or preparing or anything like that, feel free to please let me know. Um, Yeah, main things to focus on is the homeworks, and if you're able to understand homeworks 4, 5, and 6, the only other thing, like if I did homeworks 4, 5, and 6, and I was confident in how I did those, the main other thing that I would do to prepare for this exam is just practice the derivations that I could ask you. Because part of the derivations is just like knowing all of the right steps, and like I'm guilty of like having exams where they're all derivations, so I memorize 10 derivations, and then after I take that exam, that information is like gone from my brain almost immediately. So like if you end up doing that too, like that's okay. Like do whatever we've got to do to make sure that we can list out the steps and go through those derivations if they're going to be a part of the exam. Um, so I was kind of reviewing while I was going through the guide. So I kind of already said some of the things that I wanted to say while I was reviewing what we did last time. So like I think I basically said all what I wanted to talk about on the kinetics equations. Um, Ultimately, the reason we care about these kinetics equations is because they tell us how our reactor will respond to some reactivity change. And there's a lot of things in our reactor that could change our reactivity. So these are just some of the different things that could change the state of our reactor, which could affect the reactivity. And a lot of these variables are coupled. So one change can affect a lot of other changes. And that's part of what we want to be able to understand with these point kinetics equations. So the solutions to these equations is a bunch to the point kinetics equations is a sum of exponentials. If we have I plus one equations, we're going to have I plus one exponentials for each solution. The time constants in those exponentials is going to be the same. So if I write like my P of t equation and my Ci of t equation, the omega time constants are the same for both functions. And the sign, so because these functions, the solutions to my kinetics equations look like a sum of exponentials, we know that exponential functions, just from math class, they can blow up exponentially, they can decay exponentially. They are very, very fast changing functions because of that e to the power t. And the sign, the SIGN of this time constant is going to affect that behavior, right? Like if my time constants are positive, then my solutions are going to go to infinity as time moves forward. If my time constants are negative, then my solutions are going to decay exponentially as time goes forward. So we want to know what those time constants look like so that we can predict what our solution behavior is going to be. Um, the n-hour equation is how you find those time constants. So we want to know how to derive this, and we want to know how to use it to find the solutions, which are those roots, those omega k, oops, those omega k's are the solutions to this equation. So if I is bigger than 2, the number of precursor groups is bigger than 2, you can't do this analytically. You have to do graphical solutions. And so that is what we had talked about last time. So if you were to plot the n-hour equation, you're going to get a plot that looks like this. And what you're doing, so if I look at this equation, oops, rho is like the left-hand side of my equation, and then the right-hand side is all of this stuff. So this equation is a function of omega. So the input that I'm plotting on my x-axis is omega, and then the output is the f of omega, which basically has the same kind of meaning, the same kind of units or values as a reactivity, right? And so what I'm doing is I'm plotting omega as a function. I'm using omega as an input. I'm plotting f of omega, and that's giving me all these lines that look like the kind of hyperbolic sign or hyperbolic like tangent terms. And then the constant reactivity insertions are these two horizontal lines. So that would be a constant line for the positive reactivity insertion. This would be a constant line for a negative reactivity insertion. Those are labeled right here. That's a positive rho naught. That's a negative rho naught because these are above the x-axis and these are below the x-axis. Um, and so the solutions to the n-hour equation are the roots. They're the places where our right side and our left side equal each other. So all of these intersecting points, those are the roots of my n-hour equation, and those correspond these time values, or really these omega values, correspond to the values of each of these time constants. And so these are what my time constants look like if my reactivity insertion is positive. I have I plus 1. This is a model with 6 delayed neutron precursor groups. So capital I is 6. And then I have I plus 1, which is 7 total time constants. And 6 of them are always going to be negative. Omega 6 through omega 1 are always going to be negative, and then omega 0, one of these time constants is going to be positive if my reactivity insertion is positive. If my reactivity insertion is negative, then these first 6 time constants are still always negative. These guys are all negative time constants. But also, if my reactivity insertion is negative, then my omega 0 time constant is going to be negative as well. So I of them are always negative. One of them matches the sign of the reactivity insertion. If the reactivity insertion was positive, then this time constant was positive. If the reactivity insertion was negative, then this insertion is negative. And if the reactivity insertion was 0, then omega k would be 0 if the insertion was 0. That's what that dot at the origin corresponds to. So this plot is really important. That's why I'm emphasizing it so much. We want to be able to say the things that I'm telling you about these time constants. If I give you the n-hour equation and I give you the point kinetics equations and I tell you the reactivity insertion is positive, I need you to be able to tell me how many of the exponentials are going to be negative, how many are going to be positive. If I tell you the reactivity insertion is negative, I want you to tell me that all of these constants are negative. So like this graph is a really important thing to be able to internalize because it kind of contains all of the information that we need to know about what these time constants are going to look like. And if you have a calculator, if you have a graphing calculator, you can actually plot the right-hand side and you can plot the left-hand side, and then you can find exactly where those intersection points are. And you have a problem on homework 5 that gets you to do that. So these are the interpretations that I want us to be able to have, that I of those omega constants are always going to be negative. The other one is always going to be, it's the largest algebraically, so it's the one that is, closest to it's the most positive time constant is the way to think about it. That other time constant, it's always real. It always has the same sign as the reactivity insertion. And if the reactivity insertion is negative, then this time constant kind of hits this vertical asymptote that corresponds to, so I'm talking about this line right here. This vertical asymptote corresponds to the lambda 1 decay constant, the decay constant for our type 1 delayed neutron precursors. So as we were to make this bottom horizontal line is a negative reactivity insertion, and if we made that reactivity insertion even more negative, then this graph, this horizontal line would fall further and further down, which means that this solution to this omega 0 time constant would get closer and closer and closer to this horizontal asymptote. So if the reactivity insertion is negative, that omega 0 time constant is kind of bounded between 0 and negative lambda 1, which is the minimum time constant. That minimum time constant corresponds to the precursors that have the largest half-life, because the decay constant and the half-life are inversely proportionate. And if the longest half-life is 55 seconds of the precursors that we care about, then the decay constant is ln of 2 over 55 seconds, which comes out to 1 over 80 seconds inverse. So this lambda min is like the corresponding time constant that you would see on this vertical asymptote right here. And that also means that kind of limits how fast our reactor can shut down. So that's one thing that I'm going to talk about in a sec. But basically, so from that understanding that all of the solutions to these functions are a sum of these exponentials, but almost all of those exponentials have negative time constants, and only one of those exponentials has a time constant that might be positive if the insertion is positive, or might be negative if the insertion is negative, we can start asking the question of what are our solutions going to look like as time moves forward for different scenarios. So we're always going to assume that the reactor is initially in some critical state, and then we have some reactivity insertion that makes our system deviate from critical to either become subcritical or supercritical. So if we made the reactor become subcritical, that means that we're doing a negative reactivity insertion, and that means that all of our time constants are going to be negative. The only one that's going to be So if they're all negative, that means if we let time go to infinity, they're all going to start decaying away. They're all going to approach zero. And the one that's going to stay there the longest is the one that has the algebraically largest time constant, which is omega zero. So if you have a subcritical system and you ask the question, what does the system look like? What does my solution look like as time gets really big? It's going to be governed by the exponential with the algebraically largest time constant, which is that omega zero exponential. And if it's subcritical, this time constant is negative, so our solution is going to look like e to the negative um, t, like e to the negative omega t, and that means that as t goes forward, the exponential behavior is going to be decreasing, right? We're going to have decreasing exponential behavior with time, and that's the case if you have no source and you make your system be subcritical. And we're kind of ignoring that at the very early stages of that transient, we are going to have all of those other negative exponentials, which are going to be influencing our solution. They could make our solution behave much uh, drop faster or slower than what like one single exponential can do. This is only talking about the behavior of the solution at like a larger amount of time. So not instantly after, but at some later time. And how we deal with that instant part is usually we just assume that there's either a prompt jump. If the reactivity insertion is positive, there's basically going to be a little bit of a prompt jump before we follow our exponential behavior. And if you have a negative reactivity insertion, you're basically going to have a little prompt drop followed by its corresponding behavior, which in this case would be decreasing exponential. So it's maybe easier to understand if it's supercritical because that means one time constant is going to be positive, all of the others are going to be negative. So if I ask the question, what does my behavior look like as t gets very large? Any negative exponential is going to decay away. So the only one that's going to be left is the one that was positive. Therefore, my solution is going to be dominated at large t by e to the positive omega zero t, and omega zero is positive, therefore this solution is going to look like exponential growth. It's going to look like I have a solution that's growing exponentially with time. And like we were saying before, at the beginning, that might not be the case. Generally, what we'll assume at the beginning is that you have kind of for a positive reactivity insertion, that you have a little bit of a prompted jump followed by that increasing exponential behavior. And then if it's a critical reactor, that means the insertion is negative. All of our time constants are negative except for omega zero, which is zero. So our solution is going to be dominated at large time by e to the zero, and e to the zero is a constant. Therefore, our solution behavior as time moves forward is going to look constant, or in other words, our solution is going to be in a steady state. Um, so when we have a reactor that's initially critical, and then we're told there's some kind of reactivity insertion. It's a positive insertion or it's a negative insertion. We're not even really caring so much what causes the insertion, but just is the insertion positive or negative? We need to be able to know what the resulting trend is going to be. We need to know if it's going to increase exponentially or decrease exponentially, and it's just based on the reactivity insertion. Um, so that is kind of all of that was a review of last time. And one of the things that we were saying is that when the insertion was, well, we talking about the limiting behavior, actually. So we're saying that like as time moves forward, our solution is going to be dominated by the algebraically largest exponential, which was that omega zero exponential. So omega is the time constant, and we define the reciprocal of that time constant, so 1 over the time constant, as t, capital T, which is probably a similar definition. It's the period of the reactor. So um, if we think about the time, so we can think about it in terms of a time constant, we can think about its reciprocal with, so if the time, do y'all remember what the units of the time constant are? in our solution, it looks like e to the omega times time. Um, exponentials, can exponentials have units? No units from an exponential. So if t has units of seconds, what kind of units does omega not have to have? Inverse seconds, right? So in this case, omega naught would have units of like inverse seconds. In the old days, they used hours. So all your time constants were in units of inverse hours. And then that's why they call it the in-hour equation, because it's the equation that solves for those time constants. So got some bug in here. Sorry. Um, so you can rewrite the exponential solution in terms of that time constant instead. And then we can talk about the period of the reactor as like a limiting case. So we had already said that the longest lived delayed neutron precursors were about 55 seconds, and that corresponds to that 1 over uh, omega was about 1 over 80 seconds. So 1 over omega is going to be about, sorry, if I just go back because I'm mixing up my words. So if we know that our lambda min is 1 over 80 seconds inverse, this is like our omega 0 time constant. At least it's the limiting behavior. Our omega 0 is going to be limited by this time constant if the insertion is negative. So that means that this is going to look like 1 over that time constant. And if the 1 over 8, so that means that this is going to look like 80 seconds. The reciprocal of 1 over 80 seconds inverse is going to be 80 seconds. So that 80 seconds is important because it basically tells us that that's like the fastest reactor period that we could possibly shut our system down. If we were to give our system the biggest possible negative reactivity insertion we could, it would never be able to shut down faster than 80 seconds. So we've talked about how the behavior of our system is going to change when there's no source. So if the reactivity insertion is positive, it's going to be exponential increase. If the reactivity insertion is negative, it's going to be exponential decrease. And if there's no reactivity insertion, our system is going to remain in steady state. And that's what we can say about our system if there's no source in the reactor. But if there's a source in our reactor, as there often may be, it's going to change how our system behaves at long time. Um, so if we have a fixed source in our reactor, this is like a source of californium 252 or some other neutron source that's basically producing like a constant number of neutrons per second into our reactor. So if our reactor is initially critical, if our reactivity is 0, but then we add a fixed source, then instead of our population having a change and loss that are in balance, that neutron source is going to be continuously producing some extra neutrons into our population. And that means that so like if the neutron source is producing like 10 neutrons per second, then after 1 second, there's 10 new neutrons in our medium. And if our system is critical, then that means that those 10 neutrons are going to produce 10 new neutrons because the production is balanced with the loss. So if you have a fixed source present and your system is critical, what it means is that your system is just going to grow linearly based on the strength of your source. So if the reactivity insertion is 0, if you're critical, then your system will grow linearly. At whatever the source rate is. If the source is producing 100 neutrons per second, then your n of t is going to look like a linear increasing solution that is the population increasing by 100 every second. If we have a source and then we add a positive reactivity insertion, then the source is going to be like a constant, production of neutrons per second. And then because of the insertion, we're also going to have those exponentials that have positive terms. So like the behavior of our function is going to look like a constant source plus a positive exponential. And if you think about like from calculus and like limiting behavior and like which kind of function dominates over the other, if you have a positive exponential and you have a linear function, which one's going to grow faster? Or like which one's going to dominate the form of your solution if you were graphing it? Exponential, right? So that means that if you have a fixed source present, but you have a positive reactivity insertion, the system's going to blow up exponentially, and the behavior of the source is going to add to that, but the overall behavior is not going to change. It's still going to be exponential. So if the insertion is positive, it's the same thing, that we will grow exponentially. And if our reactivity insertion is negative, it's a kind of, we can make a similar argument to the positive exponential case, which is that when the insertion is negative, all of our time constants are going to be negative. So our solution is basically going to exponentially decrease. But because we have a source there, instead of the population just going to zero, the population is going to go to whatever the emission strength of our source is. So it's not going to go to zero. It's going to decay exponentially and then reach some new steady state. So it's going to eventually reach steady state if the reactivity insertion is negative and we have a source. So if you want to see the math behind where these conclusions come from, it's all in Dr. Adams' notes in chapter 7. He does all of the point kinetics derivations, but he assumes that a source is in the solution, and that's how we arrived at these conclusions. We can also just kind of think about it conceptually and get to the same place. But also, if this looks familiar, it's because it is, and we actually saw all of this stuff when we did time dependence for the infinite medium problem. I don't remember if that was homework 1 or homework 2, but you actually should have seen all of these conclusions for that infinite medium problem. And so it's kind of interesting, or maybe a little bit annoying, that after we did all of this work, we're kind of getting to the exact same conclusion that we had when we were studying a much more simple problem. Um, and so in terms of what we need to know, this is a really important slide because it tells us for the kind of reactor, does it have a source or not? And also for the type of insertion, is it positive or is it negative? What's the behavior of my population going to be, whether it's the neutron density or whether it's the power? So this is a good one to know. And you might be wondering, like, did we do all of that for nothing? Do the delayed neutrons not even matter if we added these delayed neutrons? We got all these complicated equations, we figured out what the end behavior is going to be, and then it was the same answer for the infinite medium problem. We might think that the delayed neutrons don't matter, but that's not true. And the presence of those delayed neutrons is going to influence those time constants, which is going to influence the actual more detailed um, way that that behavior goes as a function of time. So like we could consider what what the n-hour equation looks like if there were no delayed neutrons. If we had no delayed neutrons, we're going to get rid of something in the summation if there's no delayed neutrons. What of those quantities, the time constant, beta, or lambda, which of those is going to be zero if we have no delayed neutrons? Beta, right? That's the delayed neutron fraction. If there's no delayed neutrons, then that fraction is zero. So if there's no delayed neutrons, that means beta I is zero. So this whole thing is going to go to zero. And that means that our rho naught is just omega times lambda. And we can rewrite that because we have a formula for lambda, big lambda. We can rewrite that in terms of the prompt neutron lifetime. So the omega is the same, and I'm just going to rewrite big lambda as the prompt neutron lifetime over k effective. Hopefully that's okay, because that's just a definition. That's just the definition of big lambda. Big lambda is just this. And if that's the case, we can also rewrite the reactivity insertion, because by definition, reactivity is can be related to K effective too, right? Reactivity is going to be like K effective minus 1 over K effective. That's the definition of reactivity. And so if I look at this equation, I've got a K effective on the top and on the bottom. So this K effective here and that K effective there can like divide away. And then if I were to get omega by itself, I just need to divide both sides by the prompt neutron lifetime. So that means that my omega time constant, if there was no delayed neutrons, is going to look like K effective minus 1 over the prompt neutron lifetime. So if the reactor is critical, we can, or maybe slightly above critical, we could get a good estimate for K effective. And the prompt neutron lifetime is also a known number for like a traditional like light water reactor. So then we could predict what that time constant is going to be. And if we know what the time constant is, we can predict how our behavior is going to change as a function of time, with the assumption that there are no delayed neutrons involved. So in a commercial reactor, the prompt neutron lifetime is about 0.0001 seconds. And if our reactor is slightly supercritical, that means that our K is like just barely above 1, like maybe it's 0.001. Then we can use what we've said so far to ask the question, what's our population going to, how much is our population going to grow in 1 second? Or what's the population going to look like one second later? So we already know that this solution is going to look like some initial value times e to the omega t. I'll just remove the subscript there. We'll just say e to the omega t because there's no delayed neutrons. So there's just one time constant, which I'm just calling omega. And then we just found what omega was. So if that's our time constant and our system started with some initial number of neutrons in sub-zero, then we can use we can plug in our time constant, plug in t equals 1, and we can see how much the initial population has grown in this 1 second of time. So it's going to look like n naught times E. Inside of omega, we're plugging in what we had before, which was K minus 1 over LP. And if K is 0.001 and I'm subtracting 1, then in the numerator here, I'm going to have 001. That's K minus 1. And then in the denominator, I have LP, which was 0.0001. 0.0001. And that has units of seconds downstairs. And we're evaluating this at 1 second. So in for time, I'm plugging in t equals 1 second. And I have to see that, and I want to see that my units cancel, right? The seconds from LP cancel the seconds from from the variable t to make sure that there's no units inside of the exponential. And so this e to the so I'm going to have e to the 0.01 over e to the even smaller number 0.0001. This is going to look like n naught times e to the 10, right? Because we're going to have, these are off by 1 order of magnitude, and this is 1 order of magnitude bigger. So this divides in 10 times. And if I have n naught times e to the 10, well, e to the 10 is like 22,000 or something like that. So this is going to be greater than n naught times 22,000. So what that means is that if there were no delayed neutrons, if all of our neutrons were just born as prompt neutrons, what our reactor would do is that if it was slightly critical, if it ever got to a state where it was slightly above critical, then in just 1 second, the population of my neutrons could change by a factor of 22,000. And if my population of neutrons can change by a factor of 22,000, my power is like proportional to my neutron density and proportionate to my neutron flux. So if my neutron population is going up by that much in 1 second, you can imagine that my power and other quantities in my reactor are going to be increasing at a similar rate. So if our systems only had delayed neutrons, they would basically be impossible to control. The presence of delayed neutrons means we don't just have one exponential behavior. We have a bunch of exponentials that all have varying time constants. That means that they basically effectively result in the behavior of our system kind of responding slower than it otherwise would. If there were no delayed neutrons. And a slower response from our system means that our system is easier to control, which is good. Um, so yeah, you can think of the extra delayed neutron precursors as adding more negative exponential terms in our solution, which kind of dampen out this tendency for some of the solutions to like blow up to infinity. Um, so the whole point of doing this and talking about this is so that we can apply the concepts that we learned from the kinetics equations and from the n-hour equation. So we want to be able to look at some system, some reactor with some kind of reactivity insertion and be able to say and be able to like draw a graph of this is how the system behaves as a function of time. This is how like the neutron population or the power behaves as a function of time. So I'm going to show some plots that can help us kind of put together these conclusions. And these are plots that we want to be familiar with, that we want to study, that we want to be able to explain to ourselves and to other people. And hopefully we can work these into our like intuition about how reactors work and how things change as a function of time. Um, and so the first kind of simple questions to ask yourself is like, does the reactor have a source? Right? Because if there's a source versus if there's not a source, that's going to affect what our solutions look like as time moves forward. The other thing we want to ask is the reactivity insertion to our system positive or negative? Because that's going to impact also what kinds of behaviors we have. So you really only have to ask two questions, and then you have to know that slide a few slides before to be able to understand, based on these conditions, how does my system change? So we're going to start with a critical reactor, and then we're going to add a source to the critical reactor. Um, so what's being shown here are two plots. In blue, it's the critical reactor before we added a source, right? And hopefully that makes sense that if the reactor is critical, then it's in a steady state. What we're plotting here is the amount, the neutron density kind of normalized to the initial amount. You'll see this a lot with plots of the point kinetics quantities that they just plot them normalized so that if so that the initial value basically starts at 1 if you're critical, and then any deviation from that can be seen if you have a deviation. So the system, whoops, the system was initially critical with no source. And so what we see that if you're initially critical with no source, then the behavior of our neutron density is that it doesn't change with time, right? When we're initially critical with no source, I'll show it in blue because it's the same as the graph. N of t is constant, right? That's what we see on this graph. And that's the graph when we are critical with no source. Now, what we're gonna do is at time t equals 0, we're gonna like drop a neutron source into our reactor. If we drop a neutron source into the reactor, does that change the reactivity of our reactor? And that's kind of a trick question. You might be inclined to say yes, because the source is going to influence the number of neutrons that are there. But a source, when we talk about K effective and we talk about reactivity, these are defined without the presence of a source. So whenever I ask, does the source change the reactivity? The answer is always no. And that's because sources don't affect criticality. They don't affect like, so basically K effective and the reactivity are source-free terms. They are defined in the absence of sources. These are source-free terms. So the addition of a source does not change the reactivity of my system. If my system was critical before I added the source, and then I dropped the source in, my system is still critical. My production and loss operators haven't changed. I've just added a source. Um, So the behavior now is that I have a reactor that is critical with a source. So in terms of behavior, I'm just going to say critical with source. And we had already talked about in that previous slide, if the reactor was critical and it had a source, then the solution to our function behavior is going to be that it increases linearly with time. That the number of neutrons that are being produced get added into the population, and then those neutrons get reproduced, such that the neutron source is kind of continuously adding to the population and growing it at a linear rate. So this is that linear behavior that we would expect from that configuration where we're critical with a source. And notice how, like, right at the beginning, it doesn't have a linear trend. That in the first kind of initial stages of the transient, the system can have behavior that deviates a little bit from the longer term behavior. And we can also, it's kind of hard to see, but there is a little bit of a prompt jump that's being shown here as well, as a result of the fact that you are adding a source, which is kind of like instantly increasing the population from what it was before the source was there. Um, so hopefully that makes sense. And as always, if there's questions about this or about anything else, let me know. Hopefully that's relatively clear based on what we had, the kind of classifications we had given before. So the next one I want to consider is so at t equals 0, the reactor is critical. So this is before the transient. The transient happens at t equals 0. So notice before, everything is steady because before we were critical. The reactor was initially critical before t equals 0. And then at t equals 0, something happens. And in this case, a control rod is going to be suddenly removed from the core. If we remove a control rod from the core, what kind of reactivity insertion is that? Is that positive reactivity? Is that negative reactivity? Or does that not change the reactivity? So if the reactivity is positive, how is that going to affect the neutron population? Does that mean the neutron population is going to like start growing more or decreasing if if the reactivity insertion was positive? Hmm? Yeah, but control rod is being removed, right? And so, yeah, that's exactly what we would think, that the control rod is like an absorbing material. If you take the control rod out of the reactor, you're reducing how many neutrons are absorbed into that control rod. Therefore, you have neutrons that are flying around that don't get absorbed in the control rod. Maybe they get absorbed in the fuel and then they cause a new fission. So the removal of the control rod does constitute an addition of positive reactivity. And as a result of that, now we have a system that was critical, and now it's supercritical, and that means that our population is going to increase exponentially. And so on both plots, you can see that there's like a little bit of an uptick right as the transient occurs. That little uptick is what we call the prompt jump. And it's just a little uptick in the graph that is there because of the solution kind of instantly changing. And then it's going to follow more or less the exponential behavior that we would expect for a system that is supercritical. And then there's two graphs that are shown here, and this is just to show you that even if there was a source or wasn't a source, both solutions are still going to be exponential. And the real difference that the source makes is that with the source, you have a faster exponential. Right? Both the source-free and the non-source-free solutions grow exponentially, but if you have a source there, your exponential is going to grow a little bit faster than it would if there wasn't a source there producing neutrons, which are growing exponentially because of our chain reaction growing exponentially. Um, so that's what things would look like for a supercritical reactor. And yeah, I guess just to tidy this up, this is a slower exponential when there's no source. Hopefully that makes sense. And then the next natural thing to consider is a reactor that is subcritical. So again, initially at time 0, we're critical. So that's critical at time 0. The axis is kind of messed up here, but so basically time 0 is like right there. And so here at time 0, we are inserting a control rod. So it's kind of like the opposite story as before. If we insert a control rod, it is going to effectively remove reactivity from our system. It's going to increase the absorption, which is going to effectively mean that the number of neutrons that are free in our system is going to go down. So adding the control rod removes reactivity because it increases absorption. And then that means that we have a reactor that is subcritical. And as a result of the reactor being subcritical, if we don't have a source, then the solution is going to kind of have a little bit of a prompt drop followed by exponential decay. And so that's what we see on the blue graph. The blue graph has no source, right? No source on the blue graph. And that means that this is exponential decrease. We have a source-free subcritical reactor, so it has exponential decrease with time. And it might not look like exponential decrease, but just be aware that this is the y-axis is on a log scale. So log scale, linear graph means that that actually is decreasing exponentially. And then the black graph is the one where we have a source. So you have the same negative reactivity insertion. That means that you initially have a system that decays exponentially, but then because we have the source there, instead of our solution just dropping off to 0, it kind of levels off to a new steady state that represents like the emission of the source. So this is our behavior for a source reaching a new steady state. And that's what you get when you have a negative reactivity insertion with a source. So hopefully if me talking about like the n-hour plots was confusing, hopefully this is kind of making more sense and helping us tie together and see what these different scenarios could look like. And you guys on homework 6, on homework 5, you have some plots of plotting the n-hour solutions. And on homework 6, you have some questions that are more like this, where it's like based on the scenario, predict what the solution behavior is going to be. Just kind of doing similar stuff to what we were doing here. Um, so one of the things that we have been talking about is these different kinds of like reactivity conditions. And one of the conditions that are given commonly is called when a reactor is prompt critical. Um, what that basically means is that there's no delayed neutron source term in the point kinetics equations. So like if I were to go back to my point kinetics equations, if there's no, so S total is the neutron source. The lambda ICI, that's like my delayed neutron precursor source. So if it's a source-free reactor, the total is 0. And if there's no delayed neutron sources, then the lambda ICI term is 0. So then we just have these first two terms in the point kinetics equations, and that's what is shown here. Um, so no delayed neutrons and no neutron sources. This is what our point kinetics equations become. If the reactor is initially critical, what does that mean about the derivative of the power at t equals 0? If we're critical, that means we're in a steady state, right? And our production and our losses are balanced. So like the power of a reactor doesn't change if it's critical. Like if you have an AP1000 reactor and it's rated for 1,000 megawatts electric, if it's critical, its power is constant. And if the power is constant, then that means the derivative of the power with respect to time is zero, right? And so if the derivative of the power is zero, then that means that the left-hand side of this equation is zero, and we can probably assume that the power is not zero and that the mean generation time is not zero. So what follows is that the reactivity insertion is equal to the delayed neutron fraction. We're basically just setting this equal to zero, and then we're saying P of t isn't zero, so we can like divide both sides by P of t. And then lambda is also not zero, so we can like multiply both sides by lambda. The lambda will cancel, the P of t will cancel, and then I'll have that the insertion is equal to the delayed neutron fraction. Um, and then, so that's like the prompt critical condition. And then we can talk about if your reactivity is a little bit below beta, or if it's above beta, very much above beta. We have different kinds of ways that we can predict the time, the reactor period for those insertions. So if the insertion is greater than beta, then that means that you're going to be able to maintain a chain reaction only on prompt neutrons. And that means that your reactor period can be calculated like this. If the insertion is equal to beta, then you can find your period by solving the n-hour equation. And if the insertion is much bigger than beta, then you're going to be able to ignore the beta in your point reactor kinetics, or sorry, in your n-hour equation, and then you're going to get your period from there, where all the neutrons are prompt. So you're going to have a reactor period that just looks like lambda over the reactivity insertion. So that's a little bit about the prompt critical condition and some of the time behavior for those different insertions. Um, this is showing how a flux in a reactor would change based on various positive reactivity insertions. So the reactor was initially critical, and it doesn't really matter if there was or wasn't a source. And then, so we're initially critical, that means everything is like kind of steady at 1, and then we add positive reactivity. And notice how if we add positive reactivity, all of these trends are exponentially increasing in time, but the size of the reactivity insertion influences how fast the rate of exponential growth is. So that's the main takeaway from this figure. And these insertions are kind of similar, are given in similar numbers to beta. So for example, the insertion of 0.0065 is very close to the beta value for uranium fuel. And then, so this is showing if you have a positive insertion that's less than beta, then your system, like, it grows exponentially, but it kind of takes a while. If the insertion is equal to beta, then your solution is going to grow exponentially much faster. And then the higher beta is, the higher your insertion is relative to beta, the faster that exponential growth is. So 0.014 is like 10 times or it's a lot more than beta, so you get an even faster reactivity insertion. Um, so that's how the insertion can affect things. We had talked about reactivity and we had defined reactivity. I didn't really talk as much about the units before, so I wanted to make sure that I covered that. Um, Basically, this is a fraction. Like you're going to have k has no units, and so rho is basically unitless. Um, Commonly, though, people in the field will express rho with units that look like a decimal or like a percentage. So there's all these funny like reactivity terms. There's the Nile, which is just equivalent to 0.01. There's the millinile, which is equivalent to 0.00001. And that is also the same thing as 1 PCM. So Sometimes you'll see reactivity given in units of PCM. It's just redefining a decimal. Like if your reactivity insertion was this number, we would call that 1 PCM. Um, and also you sometimes see it in terms of dollars and cents, where a reactivity insertion of $1 means that your insertion is equal to beta. And if you are entering an insertion that's a fraction of beta, you would probably express that in cents. Um, so and dollars and cents are broken up in the same way that you would expect, 100 cents in a dollar and so on. So if you're given a reactivity insertion as a certain value, you can use all of these unit conversions to write it in different ways. So if you're told that it's 0.4, that's the same thing as 40 cents. Um, so that means that that's the same thing as zero point 0.4 times the value of beta. And then beta is just a number. Like for every fuel type, there's a value for beta. So this is a table that's in Dr. Svedkov's notes that shows for different fuel types the delayed neutron fraction, the number of neutrons the number of neutrons that are emitted delayed, the total number of neutrons that are emitted per fission. The ratio of those is my delayed neutron fraction. So that's the delayed neutron fraction for uranium fuel. It's about 0.0065, which was the value shown on that other slide. Whoa, too far. And so if I plug in that value of beta in here, then I can actually calculate what the corresponding insertion is. And so this is what the number would just come out to as weird decimals. And then this is how you can convert that into a number of PCM by just saying that number is equivalent to 1 PCM. So basically, it's just unit conversions. I will never ask you about doing weird reactivity unit conversions on a test, but if you're doing this on like the homework and they're telling you that the insertion is beta, that's how you could think about that and deal with that. Or if they said it was a number of dollars or so on, that's how you could deal with that. So the other kind of important model for us to have is the one delayed neutron precursor group model. So like up till now, we've talked about the point kinetics equations, finding solutions based on the n-hour equation. But if you assume one delayed neutron precursor group, you can get analytical solutions for the point kinetics equations. So if big I equals 1, then that means that we just have well, okay, so we know that the solutions to these equations, the equations still are coupled ordinary differential equations. One solution is P of t, the other solution is C of t. The solutions to these are still going to be the same form, so it's going to be a sum of exponentials. So P of t is going to look like Ci of t, which is going to look like e to the omega t. So every solution is just going to look like an exponential. Every solution is going to be a sum of I plus 1 exponentials, but I is 1. So it's going to be a sum of I plus 1 exponentials, but we have one delayed neutron precursor group. So that means that we're just going to have 2 exponentials. Um, in our equations, the way that you can rewrite them for a one group model is by lumping all of your type I delayed neutron fractions together and call that beta effective, or the beta with an overbar. It's basically just, you're just adding up all of your delayed neutron fractions for each group. And then you're defining a group lambda based on all of your group abundances and the group lambdas. And there's a table of values in the notes that has these A's and these lambdas for like uranium fuel, for example. Um, so if our solution is going to be exponentials and there's going to be 2 of them, then our general solutions are basically going to look like, I'll say A0 times e to the omega 0 t plus A1 times e to the omega 1 t. That's like what my P of t solution is going to be. It's just a sum of exponentials. There's two exponentials. Each exponential has a different time constant. And there's I plus one equations. I is one, so there's two total equations, two total exponentials for each term, and two time constants to solve for. And then so C of t, I'm going to say that this is some b0 times e to the omega 0 t plus some b1 times e to the omega 1 t. And so notice the exponentials that are in one solution are the same as the exponentials that are in another solution. And if this is the general form for P of t and for C of t, then what we can do is we can plug these definitions into the original point kinetics equations. We can take derivatives of P and C because it's just derivatives of exponentials, and we can do those pretty easily. And when you do that, this set of coupled ordinary differential equations becomes a set of linear algebraic equations for the unknowns of P of t and C and C bar. So in a matrix form, this is what the equation looks like. And then once you get to that form, you're going to hopefully recognize that this is like in that fun linear algebra form where we know that if we want non-trivial solutions for the system, that the determinant of that matrix, this coefficient matrix right here, has to be 0. So the way that you would find those P of T's and C of T's, and this is all in Dr. Svedkov's notes. This is in these pages of the notes. This is the derivation for the one group model for the point kinetics equations. You're going to need this on the homework. So these are basically the steps. This matrix right here, you're going to take its determinant and set that equal to 0. Whoops. Once you do that, you should get a polynomial in the time constant omega. So you should get an equation that looks like a times omega squared plus b times omega plus c equals 0. And a, b, and c are just constants. Um, this is a quadratic. There's two roots to that quadratic. You can literally use the quadratic formula to find analytical expressions for what those roots are. And then, so you can write your general solutions and you can figure out what those corresponding constants end up being. So you can get expressions for the roots, you can express the general solutions in this manner, and then the solutions are going to be kind of complicated, even though it's still analytical. And the way that we can simplify them is we can assume some approximate values for like typical nuclear reactor quantities. And that allows us to get these approximate solutions to the point kinetics equations when you assume one delayed neutron group. So on homework 5, when you are asked to actually plot the power as a function of time, these are the equations that you want to use. You're just going to use these approximate solutions. All of the values of these constants are going to be given, so you can compute what these functions are going to look like. And again, all of this is in the notes. If you go through those pages, it shows all of the details that I'm kind of leaving out here. But ultimately, this equation right here for the approximate solutions is like where your stopping point will be. So the next thing to talk about is feedback. And so like when we're talking about these transients, these are all situations where we have some change to our system, and then we're seeing how that change affects other aspects of our system. Like if we insert reactivity, how does that affect the neutron population? How does that affect the power? And generally, when you change one thing in the reactor, you end up changing other things. Like if we were to increase the fission rate in our reactor a lot, that's going to start changing aspects of our system. And so like, when we are showing our systems increasing exponentially as time moves forward, for example, you can't maintain exponential growth forever, right? These things are growing exponentially, but it can't do that for forever. At some point, something has to change to make that not happen. And feedback is one of the main kind of phenomena that's going to affect so when we talk about feedback, most of it is caused because of temperature changes. So most of the feedback in the reactor is going to be caused by temperature changes. Um, and the temperature in your reactor is going to be influenced by the rate at which energy is being produced in your reactor. In other words, it's going to be influenced by the heat generation rate. And the heat is being produced in our reactor from what reaction? What's the reaction that makes our system heat up? Fission, right? So it's the fission rate that's going to determine the heat generation rate. And as we have fissions happening, they are producing all of these fissions producing fission fragments. These things release a lot of energy and then get stopped very quickly. Basically, all of the energy emitted from fission, almost all of it, gets converted into heat, which heats up our fuel, and then that heat in the fuel gets transferred to the coolant, and so on. And the fission rate is based on the neutron flux, right? So the fission rate is determined by the neutron flux. Or you could also say the neutron density or the neutron population. Um, and so if we change our reaction rate, ultimately we're going to change temperature. So like if our system is increasing exponentially, eventually our system is going to start heating up, and then our system is going to have a response to those temperature changes. What are some quantities, like nuclear physics quantities, that are temperature dependent? Maybe quantities that are also involved in calculating reaction rates. Cross sections, right? The cross sections also depend on temperature. Recall that we had talked about, like even early in like maybe lecture one or two, like Doppler broadening, that if we have like cross sections, there's that intermediate region where there's all that crazy resonance stuff happening, and those resonances are highly affected by temperature. So yeah, the cross sections definitely are influenced by temperature, and that the reactivity and the multiplication factor depends on these cross sections. So the reactivity and K effective um, are functions of those cross sections. So if we heat a reactor up, it's going to change the cross sections, which is going to end up changing K effective, which is going to end up changing the reactivity, which is going to come back to our initial input, right? Like the initial change to our system was we had some reactivity insertion, but then that change is going to cause all these other effects, which is ultimately going to affect the reactivity, which is going to affect everything else. So these systems are coupled and they interfere or interact with each other. So that's kind of like the illustration here, that you're critical, you're at a very low power, the fission is like so low that it's not really changing the temperature of the fuel. And then you remove all the control rods from your reactor. So as that happens, it's like a very large positive reactivity insertion. The insertion is positive, so our neutron population will start increasing exponentially with time. As the fission rate increases exponentially, the heat production increases exponentially. Eventually, that fuel is going to start to heat up really, really fast. And once the fuel changes temperature, it starts affecting your cross sections. If we think back to that Doppler broadening, specifically, if temperature increases, it causes those resonances to broaden. And those resonances becoming wider means that more neutrons of more energies can be absorbed within that resonance. And that means that when a temperature increase happens, the resonances in the fuel will cause a lot more absorptions of neutrons that don't lead to more fissions happening. It's like a parasitic absorption caused by the broadening of those resonances. So that's the whole idea behind Doppler broadening. And as a result of that, the multiplication factor is actually going to go down. So if the temperature were to increase more, that means that as a result of that feedback, the multiplication factor is going to decrease. And that's going to keep happening until K effective eventually goes back to 1 and the reactor finds a new steady state. So this is an example of what we call negative feedback. This is an example of negative feedback. And negative feedback is really good. We want our reactors to have negative feedback because it gives our reactor stability. So in this scenario, it was a positive reactivity insertion, which increased temperature, but then the increase in temperature decreased the reactivity of the system. So that's why it's negative feedback, because you had a positive insertion of reactivity, and the system responded to that ultimately by making the reactivity go down. So if you have a change that gets reduced by your system, that's an example of negative feedback. If you have a change that gets amplified by your system, that's an example of positive feedback, which would be really bad. If this reactor had positive feedback, the increase in the reactivity would increase the temperature, would increase the reactivity, would increase the temperature, would increase the reactivity, and increase the temperature, and then your reactor blows up. So we like negative feedback because it means that our systems can actually be controlled, and it allows us to have stability over those systems. So in terms of like the world of feedback, you can think of our reactor system as just being, you can think of our reactor as a complex system, and it has inputs that are going into it, and it has outputs that are coming out of it. The inputs into our system are just anything from the environment that could impact our system. And then the output is how the system responds to those inputs. So what we just illustrated is a feedback loop where so you have some positive reactivity insertion. And with a feedback loop, you're showing kind of how the inputs influence the output. So we're saying this positive insertion of reactivity affects the power. This causes a change in the power. Specifically, it causes the power to increase exponentially. When the power increases exponentially, it causes the temperature to increase as well. The increase in the temperature affects my cross sections. It causes the cross sections to change. Specifically, it causes my sigma A to increase, and it relatively causes my sigma F to decrease. So if my sigma A is going up and my sigma F is going down, that means ultimately it's affecting my reactivity, and it's going to reduce my reactivity. It's going to reduce my neutron multiplication. So this makes the change in reactivity negative, which influences what I had in my system to begin with. So this is like a feedback loop, which is illustrating that scenario that we just described. And in our reactor, we almost always want negative feedback because it's going to dampen any initial disturbance that we have to our system. Whereas if we make our systems with positive feedback, any little change to our system could make the system blow up. And that would be very unstable. Um, a simple example of feedback is like, well, when we think about dampening and amplifying, like the shock absorbers in your car, that's like kind of a feedback response to a bump. And those shock absorbers, they give you negative feedback, and that bump to your system gets dampened out by those shock absorbers, so that if you were to like think about, what does the profile of my kind of vibration look like? Maybe it starts very large, but then those fluctuations like very quickly get dampened by your system. So that would be like an example of negative feedback. Whereas if you like didn't have shock absorbers on your car, or even worse, you had weird reverse shock absorbers that amplified the shock every time, then if you hit some bump, then the things would just blow up and go kind of out of control. And one little positive change would cause the system to just basically like blow up and go crazy. So that's just like a kind of way to illustrate and think about the difference between positive and negative feedback. And we always want our reactors to have negative feedback if we can afford it. Yeah. Mhm. Yeah. So in section 7, this is kind of where we're getting into chapter 7 of Svedkov's notes. Um, this is all about something called temperature coefficients of reactivity. And reactivity coefficients are numbers that describe feedback effects to our system due to a temperature change. And temperature changes our reactivity in several ways. We already talked about one of them, that the temperature influences our cross sections, which influences our reaction rates. If we have a temperature change, that can also change our materials. Like if I have a piece of metal and I heat it up, what's going to happen to the volume of that metal? Yeah, things like expand or contract. There's thermal expansion and contraction due to temperature changes as well. So if you have the same metal and you heat it up, which means that the volume goes up, what's happening to the density? The density is going down. So changing temperature changes volume, which changes density. And if it changes the density of our core components, that means it's going to change the cross sections too, because recall that our macroscopic cross sections is a microscopic cross section times a number density, and that the number density is proportional to the mass density, n subscript m for the mass density, so that we hopefully don't confuse it with the reactivity. Um, so if you change your density, that's going to change your cross sections too, and that happens as a result of temperature change. So ultimately, if the temperature in our system changes, we want to know how does that affect the reactivity of our system. And that's what the temperature coefficient of reactivity tells us. It is a quantity that tells us about the rate of change of our reactivity per some change in our temperature. So as an equation, it is defined as the partial derivative of the reactivity with respect to the temperature. And here the reactivity could be a function of time or temperature. So by definition, a reactivity coefficient, it depends on what type of coefficient it is. This is a temperature coefficient, so it's the derivative of our reactivity with respect to the temperature. We could have other reactivity coefficients where it is always how the reactivity changes with respect to some other quantity of interest. Could be temperature, could be volume, could be void fraction, and we'll talk about those things. What would the units of alpha T be? If I if alpha T is defined as a reactivity over a temperature change, what would the units of alpha T come out to? Yeah, and like so it's gonna be some funny reactivity units, which could be nothing. Or like so it could be PCM, it could be dollars, it could just be a decimal. Um, Funny reactivity units divided by temperature units, right, Shimobi? So in the bottom, we would have whatever our temperature units are. So that could be like degrees Fahrenheit or Kelvin or degrees Celsius. Yeah, it's just going to look like maybe inverse temperature or weird like PCM per Kelvin or something like that is also common kind of reactivity units, temperature coefficient of reactivity units you might see. So with this definition, we can actually rewrite the definition in terms of K effective. So how if I have how do I write the reactivity in terms of K effective? Perfect. Yeah, so it's going to be, and if I want to write it, if reactivity is a function of time and temperature, K effective could be a function of time and temperature too. So I'll say K effective of T and little t and big T, time and temperature, over K effective of time and temperature. So if I have this alternative way to define reactivity, then I can redefine my temperature coefficient of reactivity in terms of the K effective. So like I'm going to be taking the derivative, the partial derivative with respect to temperature of rho, which is equivalent to K. So I'm just going to say K minus 1 over K. And so I'm taking a derivative. If I take a derivative of this, what like differentiation rule do I have to use? You got to do a quotient rule, right? Because I've got a derivative of a function divided by a function. So if I do quotient rule, can y'all help me out what the terms are supposed to look like if I do quotient rule? So if I have a yeah, so there's going to be the way that I think about it is that if my function is a low over a high, this is how my calculus teacher taught it to me, and so I always remember it this way. Then f prime is low d high minus high d low all over low squared. Um, so in this case, the bottom, the oh, and I I put these backwards. It's high over low. So it's the basically the bottom times the top derivative minus the top times the bottom derivative divided by the bottom square. So if I think about it like that, then the bottom function is K effective. So here I'm going to have a K, and then it's that times the derivative of the top. And if I take the derivative of the top, what do I get? It's just K prime, right? Because the derivative of 1 is 0. So I'll say dk, and it's the derivative with respect to what? dt, yeah. So I've got that, and then I've got minus, and then I do the top times the derivative of the bottom. So the top is this whole thing. So I've got k of t minus 1 times what? Yeah, times the top times the derivative of the bottom. And again, the derivative of the bottom is just going to be dk dt, right? dk dt. And then that is all over the denominator squared. So, and the denominator is just k, so that's going to be divided by k squared. Hopefully that's okay. Good practice of the chain rule, sorry, the quotient rule. And then from there, what's going to happen is I can distribute this negative sign into here, and then I can FOIL this out. And what's going to happen is I'm going to have the dk dt times the k terms are going to cancel. And only thing that I'm going to have left over on the numerator is just a positive dk dt. And then in the bottom, I'm going to have k squared. So ultimately, it's going to look like 1 over k squared times dk dt, where k was a function of t and t. Hopefully that's okay. Um, and yeah, so that is how we can write our temperature coefficient in terms of the multiplication factor. Um, K effective squared is always going to have what sign? Positive or negative? Positive, right? Because it's squared. So K effective squared is always positive. So if alpha t is 1 over k squared times the derivative of k with respect to temperature, then how does the sine of alpha t have to compare to the sine of the derivative of k? Does alpha t have to have the same sign as the derivative of k or a different sign? Same sign, right? It has to have the same sign as the derivative of k with respect to temperature. So if my coefficient has the same sign as the derivative of my effective multiplication factor with respect to temperature, then if the coefficient is positive or negative, I can answer the question, how does my effective multiplication factor change due to some change in temperature? So if my alpha t is positive, that means that dk dt is always going to be positive. So therefore, if I increase the temperature of my system, what's going to happen to K effective? If alpha T is positive and I increase temperature, is K effective going to go up or is it going to go down? It's going to go up, right? If the derivative is positive and the temperature goes up, then the numerator is going to go up too. You can almost think of that as like a fraction, and if the bottom goes up, then the top is going to go up too because the sign is positive. So K effective is going to increase with increasing temperature. And that's positive feedback, right? You make some change to the temperature, you increase it, and then as a result, the K effective is going to increase as well. That would be an example of positive feedback. And if you have a positive temperature coefficient, you will get positive temperature feedback. Whereas if alpha t was negative, then that means that the derivative of my temperature is going to be negative. And that means that if my temperature change is positive, that means that the change in K effective has to be negative. So in other words, K effective is going to decrease if I increase my temperature and my alpha T is negative. That's negative feedback, and that's what we want to have. We want to see that the K effective or the multiplication of my system goes in the opposite direction as some external change that would make my system like blow up. So generally, if you're trying to like design a reactor, you need to be able to like demonstrate that your reactor has negative coefficients of reactivity. Yeah.
Right. Where the actual region caused as part of the
Chernobyl.
pollution.
Yeah, in Chernobyl, they did a funny thing where they had control rods that I still don't really understand why you would ever do this, but there was actually graphite at the bottom of the control rod. So when you inserted the control rod, actually the very first thing that happens is that the graphite hits the reactor first and causes some extra moderation. Um, so yeah, if you watch the Chernobyl HBO Chernobyl miniseries, if you haven't watched it, it's really good. It's really worth watching, and I feel like that's one of those shows that we could all nerd out about because it's like you're seeing people in the show doing kind of the same stuff that we're doing right now. Um, so yeah, if you haven't seen it, go watch it. And when you watch that, you'll have a good understanding of how Chernobyl happened, especially after like actually knowing about the stuff like kind of academically. Um, so there are other reactivity coefficients, not just for temperature. You can define them for basically any quantity. You could define a pressure coefficient of reactivity, that's alpha P. That becomes significant in gas-cooled reactors, not so much in our light water reactors, because in our light water reactors, they're pressurized. The pressure is already so high that changes in pressure don't really have any effect on the multiplication factor compared to other things. Um, the void coefficient, alpha V, is another one that is really important, especially for boiling water reactors. And these coefficients are defined in a similar way to the temperature coefficient. It's just how does my reactivity change based on a change in the quantity that this coefficient is describing. So an alpha P would be the derivative of my reactivity with respect to pressure. And alpha V would be the derivative of my reactivity with respect to that void fraction. Um, so the void fraction is important because, like in a boiling water reactor, coolant comes over the bottom of your fuel rods and then the coolant rises. As that coolant rises, it boils. So, like halfway up the core, you don't have water, you have like steam of a certain quality. And so in the steam locations where you have like bubbles, um, if you would imagine that bubble of steam compared to if it was water there, do you think you're going to have more neutron moderation in those bubbles or less neutron moderation in those bubbles? You're going to have less, right? Because you basically have less water. And if you have less water, you have less material to interact with, to scatter, to slow you down. Um, so that just means more leakage and less absorption. So we will pick up on the reactivity coefficients when we move into our next lecture. Our next lecture is basically just going to finish reactivity feedback. I'm going to talk a little bit about perturbation theory, and that's going to be the last stuff that we talk about before our exam 2. And I'll post homework 6 tonight, or I'll post homework 6 really soon so that you can get started on that. That's going to be the last couple of things that you'll see for exam 2. So thank y'all for your time. If y'all have any questions or need anything from me, let me know. If y'all are going to be at the help session on Friday, I'll see you then. Otherwise,
Yeah.
yeah.
There's still some.
I thought he was going to take it on Tuesday of this week, which was why I said I was going to have it for y'all on Thursday. Yeah, it's not ideal for sure. I wouldn't do it that way. Um,
But you still have to grade them, so
yeah.
it wasn't his fault.
Yeah.
Yeah.
Yes.
The finals, I was going over them, and trying to see if all 3 classes are on the same day.
Okay.
So I was wondering if there's any way I can take it before or after. the
Yeah.
6th. If that, I will be sending an email.
Yeah, send an
with the-
email.
Yeah, sent out, but because I'm trying to work with all 3 professors, the best opportunity would be one day each.
Yes, for sure.
But if,
Yeah, I'm flexible with that. Just send me an email and I guess let me know if you have a preference. Otherwise I'll just kind of I'll have to think about it in terms of like, do I want it to be before or after?
right,
But yeah, I can help with that.
if there is like really good flexibility, I would like to
Yeah,
see
I
the
mean,
other
yours
professors.
is already in the testing center anyway, so it's easy to just say like, I'll just put it on this day instead.
Right, yeah, because it was already confirmed, like all three, there's no time conflict, it's just.
Yeah,
I-
it's just hard to
9
prepare
to
for 3
12.
exams on the same day. That's crazy. Yeah.
Yeah, my mom was.
I somehow always ended up lucky and like I never had maybe there was like once I had 2 finals on the same day. Yeah, that sucks. I can try to help alleviate that in a little bit of a
Perfect,
way.
thank you so much.
Yeah.
Could you go back to the slide where it was like 80 seconds for the reactor shut off?
This one?
Yeah, so I was just confused on like what
Yeah.
this means because we were looking at the graphs of like the concentration and you get the prompt jump like right after the insertion.
Uh-huh.
And I guess I was assuming that like this 80 like it would take 80 seconds before you'd see anything.
Yeah. So it's basically that. So if this is my function, if my function looks like P0 e to the t over big T, and big T is 80 seconds, really this reactor period means that in 80 seconds of time, I would have e to the 80 over 80. And then so basically it would mean that in that time, my population would change by a factor of e. That's effectively what that is saying. It's how long it would take for your population to change by a factor of E. In this case, if it's like a negative reactivity insertion, how long it would take to decrease by a factor of E. Does that make sense? Okay.
So so like changing the period would be
Yeah.
That's like, I guess like pretty essential, I guess.
Yeah, so it's mostly telling us that we're kind of limited on how fast we can shut it down based on that the decay constant of our longest living delayed neutron precursors. And so basically kind of what it means is that like if you had some plot where this is power, like kind of normalized power versus time. And if I was starting critical, so this was like starting at 1. Um, and then we're saying like we got some kind of negative reactivity insertion that is resulting in our system like going into a shutdown. So if we had a negative reactivity insertion at 0, then kind of like what you're saying, there'd be a little bit of a prompt drop from that. And then we would have exponential decrease. And then all we're saying with that time constant is that this capital, if this is capital T, then that point, going from 0 to T, the height of my graph has dropped by a factor of.
Okay.
Yeah.
Okay, that makes sense. Just real quick, like what is a prompt jump like, I guess physically? Like, how would you describe it? Explain that.
I kind of think of it as just like, it's kind of like a step change in your system. So like, if you have P over P, and this is T, then if I'm starting at 1 and I have a positive insertion, then basically what's going to happen is you have all these time constants that we're kind of not really calculating in depth. And we're just kind of saying that in the first couple of seconds, if the insertion of reactivity is positive, then my system is ultimately going to respond by increasing. And so I would approximate that with a little prompt jump that's just like a little uptick, followed by like the increasing exponential behavior if your insertion was positive. Whereas if your insertion was negative, then it would like have a little bit of a prompt drop, followed by an exponential decay. So that would be if rho was.
Okay.
Yeah.
Okay.
So yeah, that's how I think about it. Just like a little instantaneous change in whichever direction my reactivity swing was.
Okay, thank you.
You're welcome. Thank
I'm gonna. So the period of the reactor, I was gonna ask you about
Yeah.
this. That is just dropping from that point to that point. It's not about like how long, like it's not, if you do any insertion, that's how long it's gonna take.
No, that's like the maximum time that it would take to shut down, or how much it would take to change by that factor of factor.
And then on the last slide, you were talking about the heating in the film.
Mhm.
Does it form a film around the rod itself? Or
Yeah.
okay, so does turbulence help that?
Yeah.
As like,
Yeah, because so basically, one of the coolest things that it's basically exactly what you're asking. There's a thing called critical heat flux. Um, and this is a thing that they actually can do at Idaho National Lab, where they basically have a fuel rod, and then they can pass a very high heat flux through it, and you can visualize how the bubbles form around the rod. So it's not wanting to zoom in, but
yeah,
um, but yeah, so like initially, ideally what you want is not that. Like once that happens, you are in big trouble because the steam is like a very bad conductor. So once you get to this is the critical heat flux where you basically have so much heat being deposited from your fuel that it just like instantly vaporizes everything around it and you get like a vapor blanket that insulates the rod and then the heat just builds up and it will basically like you get kind of runaway if you're like in a reactor if like a fuel rod melts or something, especially in a boiling water reactor. It's kind of these kinds of things that we're worried about. And so yeah, and the turbulence makes a big difference because ideally what you want is for things to be like mixing, and that's what the turbulence allows for.
With, okay, so. I was gonna ask, so like boiling water, so not pressurized, but would,
They're slightly pressurized, just not as much. They have a pressure such that the coolant can still boil in the main loop. I don't know if you've ever looked at like because reactor loops, it's like you've got like a primary loop,
right,
and then you've probably got like a heat exchanger, and then you've got like a secondary loop. That's like what normal, like that's what a PWR looks like. A BWR is just one loop.
So you're
Because
gonna-
in a BWR, your reactor is basically also your steam generator. And so you get like low quality, you get water that comes in, and then you basically get like steam that comes out.
so that would be this heat flux would be a constraint of BW?
Boiling water.
Yeah, okay.
Yeah.
Well, that's fun.
You'll learn about this in the senior design class. Either Dr. Kirkland or Dr. Weir. It's all about thermal hydraulics. So it's kind of like it's all of the stuff that we're talking about in reactor analysis, but then it's coupling that with heat transfer to understand, to better understand things like this. Yeah, that's like kind of putting it all together.
Cause your research, or what you're working with. Kimber, right?
Mhm. Yeah, so this is my stuff.
I like this.
Me too. Yeah, it seems it's the fun stuff, and that's what everybody really cares about, right? Is like how do you produce power, and also how do you make stuff like not blow up or whatever.